talking about multi-layer designs, stackups, layer stackups, vias, talk of burried vias, talk of blind vias, and more on layer stackups. So when we talk of multi-layer or layer stackups, we are talking about what's the arrangement, what's the configuration that's adapted. Say when you are doing a PCB that's more than 2 layers. So multi-layer, we are talking of 4 layers and above. So there are specific stackups and of course factors that we do consider when we are doing multi-layer PCBs. So we were talking about this, the arrangement, the kind of arrangement that you select for, say, 4-layer PCB, 6-layer PCB, and how you adopt such layers, and what are the factors that maybe could lead you to migrate from a 2-layer PCB to a 4-layer PCB. I'm quite sure that even if there is one or two of us or any one of us that have probably been able to do like a 4-layer PCB, a multi-layer PCB, they probably might not have had enough reasons or why would they have chosen that particular stackup. So this class tries to expound on that and what are the factors that may lead us to such setups and how we select them. So I've given some few examples here on how on some of the KiCad designs that we have managed to do. This is a 4-layer stackup. Of course, this is also a 4-layer stackup. We're having a very advanced board here, having custom outline shapes and stuff, also having 6-layer board. So it's a very advanced board, HDI board. We are talking of high density interconnect here. So it's a very good example for us to learn from and what was done in that particular board. You see, as you can see closely, it also had BGA stuff and stuff like those. So it's a good reference for us. So the first layer on the PCB, this is what we always call the top layer and the bottom layer. So top and bottom. So we have the first layer and the last layer. We have the top layer and the bottom layer. So in between is what they call the prepreg. And this is what you would see in most cases as we call the material that's used in to separate the different layers. So of course we have different types, and of course it will again be determined, say, by the maximum thickness of the board that you wish. Remember we talked about in the previous class, we discussed about the thickness of the board and how you might select one for that. What are they? And of course the boards that we do have as, say, the default sizes, say, of PCBs and stuff like those. So what we'll be doing in this class, we're going to expound on this and even the minimum, say, the minimum thickness of a particular PCB, say, if it's multi-layer board. Yeah, because of course, if you're doing multi-layer board, again, we have limits, say, until what size we can make our board smaller. Because again, if you're going for a multi-layer PCB, I know you want your PCB to even be much smaller. It's because you have maybe constraints in terms of space, say that, maybe some signal types and stuff like those. So let us actually proceed and go ahead and see what are the considerations that we might get into while we are opting for multi-layer stackups. So in this case, the first point here being signal types that are available for us in our design. So maybe our board is an RF signal. Say we have some clock signals there that we want to keep separate or something of the sort. Say we have some audio signals, maybe it could lead us to do that. Say we have like memory lines on our board. So the signal types actually, they do really determine whether we are going to go for multi-layer or just go to, say, like 2-layer board. Different power lanes. So this is most oftenly found on FPGAs and BGA packages. So say you are dealing with a particular FPGA, say one like for image processing, you might find that BGA to have like several power lanes. And what do I mean several power lanes? Most BGAs, you find that it has like 2.5 volts, 1.2 volts, 1.1 volts. So these power lanes are very different. And again, you might want to create, say, some zones for that particular power. And of course, to do that, if you have a dedicated, say, layer that deals with power, you'll again have like good return paths, say, for power. And of course, you have sufficient ways in which you can power your BGA. And of course, also tap that power to different parts of your circuit. So power lanes, actually, if there are very many, it's always good to have a dedicated plane, say, for that. And of course, you cannot have this, say, in a two-layer plane, a two-layer board, that is. So power reference plane. So I mean, for if you're going to go now for a multi-layer board and say you want to have like every signal, where every signal should have a reference power plane. And when I say reference power planes, I'm talking about VCC and ground. So also, these are things that you have to consider. I don't want to get much deeper here. I know now it's becoming complex here. I want to just go like now touching on the top, so that at least you don't get lost in the middle. Type of application. So you find that boards like high-speed boards, RF boards, memory boards, say like audio and video signals. So these are things that might lead us to having to work with four boards, because of to four layer stackup, because of some of the things that we might opt for. So let me touch on a four-layer stackup, because when I say a stackup, and what do we mean, like, and how, and what are the advised ways or practices that you would lay out a four-layer board, and where we choose such stackups. So when we have a four-layer board, say the top layer, which is layer one, should always go for signal layers. And I'm talking of any signal that is within your board that's a signal layer. Say like any connection that's not power, and it's not power and not ground, all those are signal layers. Like say signals communicating between different ICs, say from the MCU to some other component. So all those signals, and of course always we say try to fill as much as you can all your signal layers to go on the top layer. So what happens on the second layer? You want that every signal layer to have a reference power plane. So that's why again on the second layer we will always go for a ground signal or a power signal, because we wanted to have like a reference plane. Very important for signals to have some reference planes. And you will see how this comes in handy when we are doing signal integrity, and maybe when we are facing issues such as EMC and EMI. So you always want your third layer to be VCC, and this is also power. And if you're having your signal is the third signal as that, you also want your bottom layer to be a signal layer, so that at least again we can have a reference plane, say for that signal. So you can see the way we are placing these layers is that wherever we have a signal layer, we have a reference plane just next adjacent to it. Very critical that it must be adjacent to it. Well, of course, there are times where you can see someone doing signal. Well, they might be allowed, but the ideal stackup that will give you some very good results is this kind of setup. And I'll show you how we do this in KiCad and how we are going to set it up and stuff like that. So what you do is that you have your, and of course, when you learn how to work with four-layer stackup, I mean, you're going to get spoiled, because it's you just do a via there, just draw a small line and a via, and boom, you've connected power. Say in like 3-4 vias, you have all your powers connected. So again, these are stackups that make some designers in the early stages get spoiled. Say when they are designing and stuff like those, they might seem like complex, but once you start doing these four-layer designs, you want to do four-layer for everything, and of course you're making your design to be much expensive. So of course there are caveats when we go for four-layer designs. So again, it's not something that you should be going for each and every day. Let's talk about 6-layer stackup, so that this idea of reference plane might stick up on you, and of course you might see how it plays a big role, and how at least we can actually play with this signal and of whatever power and stuff thing. So for 6-layer stackup, you see the first layer, of course, you do signal, go for second layer, do a reference power plane, go for ground, then go for signal again. Then you see this signal has a reference plane here, which is ground. Again, the signal next here has a reference plane here, which is power. Yeah, you see power, of course, here. Then, of course, we have the 6th layer, a signal. So you want to have your 5th layer, the layer next to adjacent to your signal, as a reference plane, of course. So these are very critical, of course, and how we'll be doing this. And again, you don't have to memorize this. This is something you'll just know like you just need to have a reference plane next to your signal layer and something like that. And of course, when we have power and ground just next to adjacent to each other, also this is very good because we'll be having very short return paths here. Remember that we talked about return paths. This is the flow of power, say from VCC all the way, because it's going to flow all the way to ground. So remember that we want to make sure that we are having the signals now coming in very well, so that we have very short return paths. Once you have very huge return paths, remember we are creating inductance there, and of course your design may fail to pass EMI and EMC tests. So I'll of course show you how to set up these kind of setups on KiCad. So maybe let's now stop doing the theory. Maybe let's first set up on KiCad and see how we do that. So remember our design. So I'll do that on our previous design so that you can see even how you can change maybe a 2-layer board into a 4-layer Stackup. Say maybe you are designing, you thought, well, 2 layers might work for this board, but then moving forward, you realize that, well, all my traces cannot fit. So several factors that might lead you to going to 4-layer board or 6-layer board. One is if you have so many signals and they cannot fit on top and bottom. So maybe this is a good chance for you to take some few notes. So it's when we have layers, when we have a lot of signals and they cannot fit on top and bottom. Say when we are having so many components here, and of course they take a lot of space. They take space on their double-sided board, so it takes a lot of space on top and bottom. And so saying that on top and bottom you have very few areas that are left, you have very few real estate left, say to do the routing. And of course you will have to do that on the internal layers. The other thing is that say if you have some complex designs, say like you have RF, and of course say like you have audio and you have some high-speed signals, that of course, because when we are dealing with RF, when you are dealing with high-speed signals, you'll be always go for 4-layer signal. It doesn't matter the size of the board, even if you have as much real estate as possible, but for you to get some good grounding, for you to get some good return paths, and to get some good signal integrity, you'll have to go with 4-layer for such type of boards. So what you're going to do, I'm going to on our design, so I'm going to open to fire up the board file itself. So to change your board into a 4-layer board, say we've seen that our components now they cannot fit, and at least, so I mean we have routed the board, we are at a point where we can't route this board again on 2 layers. Our top layer is filled up and our bottom layer is filled up. So what you just go is you go to file here, go to board setup. So file, board setup, it's there. And of course, you'll come here. You see here we have copper layers here. So just hit on here. You can just hit here or just anywhere within that. So say we want to go to 4 layers, just check 4 layers. Board thickness here, I told you like the default board thickness is always 1.6. So again, if you're having a board that will be having like special requirements, say you want it to be much smaller or maybe thicker, in most cases I know it's smaller, maybe 1 mm, it's good to change it here, because when you will be exporting files like step file that your mechanical engineer wants to deal with and you want to preserve the thickness, then it's something to consider that you may have 1 millimeter here. So you realize that immediately here we have front copper now, we have inner copper, we have in 1 and in 2, and then we have bottom copper here. So let's say we change this to 6, you realize now we have in 1, 2, 3, 4, 5. In 1, 2, 3, and 4. Then we have top and bottom as always. So if you go all the way, even if you go all the way, say to 10 layers, so you realize that on the internal layers, they just keep on increasing, yeah? But again, it's very important for you to note this. And this where now KiCad comes in as a very good software, because we can do up to 32 layers, and this is an open source software. This is stupendous. And of course, I'm thinking when we will be going, say, for 32 layers, well, you might be designing something that's dealing to go with space or something of the sort. Because say, even if you're going to do a very complex board, say in several years to come or several months, it could be an eight layer board, say 8 layers or maybe 12 layers. But say for this session, let's do say like 4 layers. So again, KiCad is also very good. So we can rename these layers, and of course we can select the type of signal that we want it to be. But for this type here, I don't want to select a specific signal because it might give us some errors, say on DRC. So what you will do here, for you can rename these to, you can call these, maybe let me just make it to remain to in1, but we want this to be ground. You can just add ground there, and this one we can add VCC, or maybe you can do power or VCC, whichever you like, so that at least you can know what does that into mean and stuff like that. So when I hit OK, then that's good. I'll hide the fab layer here, so at least I can have. So see what happens on this side on your KiCad. So we have these 2 layers coming up. We have ground in 1 and we have power in 2. So these 2 layers on your PCB now, we'll be having now a 4-layer stack up here. So one of the best use cases, like I told you, what we are going to be doing is we can set now this layer now to be just ground. And how do you do that? So you'll come to you will add field zones here. Just hit the layer you want. So I'll hit this layer, then I'll hit this, add field zones. Then you'll add a copper zone, area zone, as we did on previous boards. So just hit here. Then you'll select the type of signal, and which signal do we want here. For this layer, we want to use ground. So you'll just do this, and this. So just left click, and then finally hit close zone here. So if I can hit this one to show, so you see this one says show field areas in zones. So if I can hit that and I have my second layer selected, you can see we have ground here. And of course now even before hitting B here to refill, you see we have our grounds now. They are connecting with, this is what we call spokes. For those of us who don't know this, they are called spokes. So this type of connections that come up around some through hole vias or through hole pads. This one here, these are spokes. And of course you can adjust the size of this. I think I can do that. I can showcase that. So say you want to select this particular layer and you want to do some adjustments, you can just hit E here for edit, and then we select the layer we want. We want zone ground 1 proper here. So you see the spokes, demo spokes here. You can adjust this. So let's make them smaller, so at least you can see how this plays along. So I can do 0.2. And of course, I want you to see what happens here. Let me just cancel first so that I can have this in a separate place, so at least you can have a good view of this. So I'll hit E again for edit, then hit this one. So you can see this side here. So I'll do 0.2 and hit OK. So just observe what happens here. So thermal relief must be greater than the minimum width. So what we are going to do, let's have 0.6, 2.6. Of course, this one is greater than this now. So you'll see what happens here. You'll see they've just been much thinner, and you can see they're even thinner now than the top layer, as you can see here. So basically, that's the function of the spokes. They are very good, of course. This is where now at heat is now released in this. And of course, but you want your thermal spokes, of course, to be bigger for good results, of course. So of course, you can go with the 0.5, or maybe you can go with something bigger, say like 0.8. You can hit OK. Of course, you'll see that they will now be much bigger and stuff. So again, if you want now to do the top, the VCC, say the power, you can just hit this, select this. Again, left click, left. So you'll again, it will prompt you to select which power. Let me show you a very interesting tip here now. Say you don't want to select that. You remember this tool here that shows us highlight net, yeah? So you hit this, say, let's say we want to use our internal power as 3v3. So what you do, usually do this, Let me start again. Select this tool here that says highlight net, hit here. So by this means we've selected 3v3. So what you do, come on and pick this tool again, the add field zones. So when you hit here, it will have automatically selected the net name for you. You see, it has selected for us 3v3. So you will not do anything. You'll just hit OK. And of course, you see it retains the previous settings. So we can leave it this way, like we said in the previous design, say for in the previous selection. So just hit OK. Then you just go on saying left click, and then left click, and then hit on close zone here. Yeah, so what happens now, if I hit now, remember to repair your copper on your PCB, you hit B on your keyboard, B to repair, like to make sure you refill again. So I'm hitting B here on my keyboard. So again, if I can say show zones, you see here where we have now 3v3 now, you see it's connected now to this layer here. This is our internal layer that deals with power now. So, and of course, you can see to get better connection now using the spokes, we will have now gone for a smaller size, because if we reduce the size here, maybe we can have some good clearance. And of course, maybe we can reduce the clearance so that these ones can fill in. Of course, those are some of the things that you can do. And of course, that tip I've shown you here, it just makes you work quicker and stuff like that. Okay, so maybe another tip here, just remember, just so that we are interacting still with the tools to do with KiCad and of course the PCB side and in touch. Say you want just to show like a specific signal here, like this one on top here. So what you usually do, say I've selected this signal here. You can hit this tool. You see this tool here called high contrast display mode. If I hit this tool, it's going to gray out all the other areas. And of course, it will just leave the selected one as active layer. You see, I mean, and it's a very good tool. Say when you want to check out like which layer is the signal that I'm working with connected everywhere or not. So it's also a very good tool that comes in handy here. So maybe another tip while we are at internal layers is that, and of course, when you want to deselect that, just click the high contrast display mode again, and of course it will just disappear. So because maybe you don't have like, you see like our 3v3 layer, it's just here. And again, we have 5 here, which is also power. So what you can do, you can split these copper power planes. So what we are going to do here is we can have our copper plane here, the 3v3 one, coming all the way, say, up to here, somewhere here. So what I've done here, I've just clicked this and just moved my mouse. You can just left click and move it. So we can have it up to there. So maybe I can align this just to keep it neat, not for any design reasons. So if I hit now B to repair copper, and then you can see now we just have it filled until this point. So maybe what we want to do is that we want to have the 5V now selected, now going all the way to this other region. So again, this is now showing you that you can have filled zones even in different power planes. Remember that we talked about different power planes now, and of course you can see it's even coming out even if you're not dealing with FPGA. So what I'm going to do again, I'm going to take this tool again. So I'll select the 5V so that I want to use that so that you can be faster a little bit. So then select on this one here, and then come on, hit anywhere on the PCB. It's going to select 5V, then say okay here, then just throw it inside here. So I'll just come and highlight it here and hit here, and then come on here and close zone. So if I hit B again and then hit show here, so I hit B and show. Well, great. You realize we cannot see it now, and it's a good feature that we cannot see it. Why can we not see it? I mean, you realize, well, we have drawn it and it's 5V because if I double click on this signal, well, again, to check the properties, you will see it's telling us it's plus 5V, but we cannot see it. Well, this is because we don't have anything on the PCB that's connected to that particular zone. And to have our design now connected, the 5V connected to that, it's very easy. So what we are going to do is, let us take 0.5 track size here and take our route tool here, then just hit this and then just hit V for via. And this is why I was telling you are going to get spoiled, because what I'm going to do is that if I just hit this, like just V, and now hit B, now let's say show zones, and now we select the internal layer, which is power layer. Now you can see we have everything shown here, because we have at least one connection that's now being connected to the internal power plane. So what I'm going to do is to show you now how it works practically. So because if we have that, we don't need the traces themselves. So I'm going to delete everything to do with 5V on this board and then just do it using VS. So remember the tool to just select everything that's connected. Just select one trace here and hit I on your keyboard, then hit backspace or delete on your keyboard. So this is where now you get spoiled. Why? Because you just connect this, do a via here, that's already connected, do this and do a via, it's connected to 5V, do this, a via. So I'm hitting V on my keyboard, just doing a small trace here and hitting V, again a small trace here and hitting V, another one, and do see what's happening here to our unrouted here, then a small one and hitting V here. So, and you see we have 0 unrouted, and we don't have any trace running from here to here, because we have everything in the net and we have connected them through vias. So it's a very good way of working with traces. And of course, remember, as we did on ground on the previous one, so even if you have your ground as internal layers, you don't have to do like manual routing and connecting all your ground together. You just have to do a small via to ground. You just drop a via anywhere and you have everything connected as we are having it now here. So that's at least a practical way of how we can do this, say, in dealing with stuff like those. Say one more thing here, I'll highlight one more thing here, and it will come out as a very interesting tool here.